What's up, people? It's DevSage here, and this is the second video in my JavaScript data structure series. In this video, we'll be going over linked lists. So what is a linked list? Well, a linked list is a very simple data structure. A linked list is just a sequence of elements where one element has a link to the next element in the list, which has a link to the next element in the list and the next one and the next one and so on and so forth. A linked list can pretty much contain any data type, strings, characters, numbers, etc. They can be sorted or unsorted. They can contain duplicates or all unique elements. So linked lists look kind of similar to arrays, but there are some differences. One of the main differences between linked lists and arrays is that elements in arrays are indexed, meaning that if I wanted to access the third element in an array, I could just say array at index 2 with the brackets. Elements in linked lists are not indexed. So if I wanted to find the third element in a linked list, I would need to start from the head or the first element in the list and work my way through until I found the third element. Linked lists, unlike arrays, are not built into JavaScript. This is a data structure we'll actually have to create ourselves using classes. So up until this point, we've been talking about singly linked lists, or linked lists that only move, I suppose, in one direction. One node has a link to one other node. There is another type of linked lists called the doubly linked list, which is a linked list in which each node has a link to the next node, but also has a link to the node that's behind it. This double connection allows the linked list to be traversed both forwards and backwards, unlike the singly linked list, which can only be traversed forward. One real-world application of a linked list might be a music player, where each song in your playlist is an element in the linked list, and each song has a reference to or a link to the next song in the playlist and a link to the previous song in the playlist. In fact, the music player might be considered a special kind of linked list called a circular linked list, where the last song has a link back to the first song and the first song has a link back to the last song. So that's just kind of a real world application to kind of give you a better understanding of how a linked list might work. So some common linked list operations are append, which add elements to the end of the list, prepend, which add elements to the beginning of the list, delete, which removes an element from the list, and search, which basically finds an element in the linked list. So let's go ahead and jump into the code. Alright, so how do we build a linked list? Well, like I said earlier, linked lists are not built into JavaScript, so we have to write our own linked lists using classes. So what classes do we need to create? Well, we need to create a linked list class that represents our linked list, and then we need to represent a class for our nodes in our linked list. Each node is going to have a value and a link to the next node and the previous node in the linked list. The linked list will be a list of these nodes that we create. So let's go ahead and jump into it. Let's create our node class. So let's say class node, and let's give it the constructor, and each node is going to have a value. So we need to say this dot value equals value. Also, remember, each node is going to have a reference to or a link to the next node in the list. So we need to say this.next. And when this node initially gets created, it's not going to have a next value. So we're just going to initialize this to null. And we're actually going to do that for this.previous as well. So this node is actually not going to be pointing to any node, and it's not going to have a pointer to any node behind it when we first create it. Our linked list class is going to handle changing those pointers around. But that's pretty much it for the node class. Each node in the list is going to have a value, a link to the next and the previous nodes. The types of these, by the way, are just going to be nodes as well. So just in case you were wondering. But let's go ahead and create our linked list class. So let's say class linked list. And let's create our constructor. And here we're going to initialize, well, basically this linked list is going to need to keep track of the first element in the linked list, known as the head, and the last element, known as the tail. So when this linked list is first created, there are going to be no nodes in this list. So we need to initialize our head and our tail to null. So let's say this.head equals null and this.tail equals null. Okay, so let's start working on a few of our linked list methods. If you remember from earlier, one of our methods was append, which takes in a value and it creates a new node in this list at the end of the list or at the tail of this list. So let's go ahead and create that. So let's say append, and we're going to take in a value, and the first thing we're going to want to do is we need to check to see if this linked list is empty. If it is empty, then we need to create the first node by just assigning the head and the tail references to a new node with the current value that we passed in here. So we need to say if not this.tail, if this.tail is equal to null, then we know that our list is empty. Then we need to say this.head equals, let's put this in braces here. So this.head equals new node value. And what we can actually do, we need to assign the tail to this value as well. So we need to say this.tail equals this.head equals new node value. That way we can just assign the head and tail references to this brand new node here. And that's pretty much all we need to do in the case that the list is empty. Now we do need to handle the case where the list is not empty. So we need to say else. So if we're here, we know that this list has at least one node. So what we need to do is add the node to the end of the list, changing any pointers or links around as we need to. So what we need to do first is we need to store a reference. Since we're adding a new node to the end of the list, we need to store a reference to our current tail. So let's do that. So let's say and I'm going to call it old tail because this tail is eventually going to be changed, but we're just storing a reference to our current tail. So let's say this.tail, but we're just calling it old tail because eventually we're going to move this reference over to the new node. So what we need to do now is we need to move the current tail over to a new node. So let's say this.tail equals new node with the value. Okay, so what we did here, we've just moved our tail pointer to a brand new node that's not in the list. This node is currently stranded. It doesn't have any pointers to it, and it doesn't have any pointers from it. So we need to link our old tail here to point to our new tail that we just created here. So we need to say old tail dot next equals this dot tail, our current brand new node that we created. So now we've just added a new node to the end of this list, moving our tail pointer over to it. But we also need to take care of our previous pointer, right? Because nodes, remember, nodes have a previous pointer as well that points to the previous node. So all we need to do is say this dot tail, which is currently the end of the list, dot previous equals old tail, right? I hope that makes sense. So I'm going to write some comments here so maybe you'll understand it better. So the first thing we need to do when we want to add a new node to the end of our list is we need to store a reference to our current tail of the list. So store reference to current, I'm going to put current in quotes, so current tail of the list. Now that we have our reference to our current tail of the list, we need to move our tail pointer to a brand new node. So move tail to brand new node. Now this node is stranded. This node is technically not in the list at this point. We need to create a pointer that goes to it from our old tail to this current node, our new tail. So that's what we're doing here in this line. So create next pointer or reference to our new tail. That's what's going on here. And now we need to also create that previous link from our new tail to our old tail. So that's what we're doing here. So create previous pointer or reference to our previous tail. So that's pretty much it when it comes to appending. And prepending actually works very similarly. We just use heads instead of tails and tails instead of heads, but I'll show you that later. So how do we know that this works? Well, we don't really have a way to actually even print out any values from this linked list yet. So let's create a print method in this linked list that goes through the linked list and prints out all of its nodes. So let's say print, and we're going to want to take a node reference and move that reference over every single node in this list. We're going to call that reference current, and we're going to set current equals to this dot head. We don't want to use this dot head directly because we're going to be moving this pointer and we want head to stay the same. So we just assign a new variable to equal head instead. So now that we have our brand new pointer here, we can loop through the elements of the list with a while loop. So we need to say while current not equals to null, console log current dot value. Now that we've printed the current node's value out, we need to move to the next node. So we need to say current equals current dot next. And now current will equal the next node in the list. It's going to point to the next node in the list. And if that node isn't null, it's going to print out the value, and it's going to reassign current to equal current's next node, because remember, each node has a link to the next node in the list. And it's going to keep doing that all the way until current reaches a point where current is actually null. And then it's going to stop. So by that time, it should have printed all of the values out for all of the previous nodes in the list. So let's test that out. So let's go down here and let's create a new instance of our linked list. So let's say const list equals new linked list. All right, so now we have an empty list. Let's append some values or nodes. So let's say list.append 1 and let's append 5 and 8. So now let's print out all the values in our linked list. So let's say list.print, and let's run this. So let's say node index.js 1, 5, and 8. Cool. So if we wanted to, let's say, append one more value, let's say 10, we reran this, 1, 5, 8, 10. Things are working as we expected. So let's go back up here and let's add a few more methods to our list. Let's add prepend. So what this does is this adds an element to the beginning of the list. So let's say prepend. It's going to take in a value, and again we need to check to see if this list is empty. If it is empty, then we need to just assign the head and tail pointers to a new node, and that's it. So let's say if not this dot head, then this dot head equals this dot tail equals new node with the value that we passed in. Else, that means at this point this list has at least one node in it, so we need to do something kind of similar to what we did up here with append. We need to store a reference to the current head. So let's say let old head equals this dot head. So let's say store reference to current head. Now we need to move the current head pointer to a brand new node. Like up here we were moving the tail to a brand new node, but here we need to move the head to a new node. So let's say this dot head equals new node value. This is going to be our new head. That's going to come before all the elements of the list. So what we need to do is we need to connect our old head to our new head. So we need to say old head dot previous equals this dot head, right? Because we want to add our new head behind our old head because we're prepending. So it makes sense to move the previous reference of the old head to the new head. Now we need to create that backlink. We need to say this dot head, the new head, needs to point to the old head. So let's say this dot head dot next equals old head. I hope that makes sense. So we want to add a new node to the beginning of this list. We need to store a reference to the current head. Here we need to move the head pointer to a brand new node, and now we need to remember that this node is orphaned. There are no connections to this node at this point, so we need to create those connections. So we need to say old head dot previous equals this dot head. So connect old head to new head, and now create the backlink. So we're setting the new heads next to where the old head was. So now we've just added an element to the beginning of the list. So let's test that out. So let's go down here and let's say list.prepend 9,000. So when we print this, what we should have is 9,000, 1, 5, 8, and 10. So let's run this. And there we go. Prepend works. 9,000, 1, 5, 8, and 10. Cool. So let's add another method to our linked list. Let's go over delete, which is going to take in a value. It's going to search for the node to delete, and it's going to delete that node. All right, so let's go ahead and add our delete method. So let's say delete, and delete is going to take in the value of the node that we want to delete. So let's say value to delete. And delete is going to loop through the linked list and try to find a node with this value. And when it finds that node, if it finds it, it's going to delete it. The way a linked list deletes a node essentially is just by removing all the pointers or references to that node, effectively orphaning it so we can't get to it anymore. So let's say we need to consider the case that the node that we want to delete is the head node or the first node. So let's say if this.head.value equals value to delete, then what we want to do in this case is we want to move the head pointer over to the next node and then set the previous reference for the new head to null. So let's say this.head equals this.head.next. So we're moving our head pointer over to the next node, and now we need to basically orphan the old head by removing the reference. So we're going to say this.head.previous equals null. So now we've moved our head over to the next node, and we've gotten rid of the previous link to the original head. So we've effectively just deleted the old head. And from this point, we can return. So if we've gotten past this point, that means the node that we want to delete wasn't the head, and that it's further down in the list somewhere. So what we're going to want to do is we're going to want to maintain 3 references. We're going to have a current reference, which is going to look at the current node, a previous reference that's going to look at the node behind current, and a next reference that's going to look at the node ahead of current. So let's do that. So let's say current equals this.head, previous equals current.previous, and next equals current.next. And what we're going to want to do is we're going to want to move our pointers over across the list until current is hovering over the node that we want to delete. So how this is going to work is once current is over the node that we want to delete, we're going to change the pointers of next and previous to basically ignore the current node. So we're going to take previous's next pointer and point it to the node that comes after current, which is next. And then we're going to take next previous pointer and basically point it to previous, the node behind current. That way we're effectively orphaning current. We're effectively deleting it, even though we're not necessarily like destroying it. We're just removing the references to it. And JavaScript's garbage collection will recognize that there's no way to get to this location in memory, and it's basically just going to delete it. So let's do that. So let's say while current not equals null and current.value not equals value to delete. So while current is not the value we're looking for, let's say previous equals current. We're moving our current over. We're moving our previous over. Current equals current.next. So we're moving our current over. And now we need to move our next over. So we say next equals current.next. But the thing here, we need to make sure that next isn't going to be pointing to a null reference. So whenever we're nearing the end of the list, we need to make sure that next is actually not a null node. So let's say if current not equals null, then set next equals current.next. Otherwise, we can get a null reference exception. Okay, so at this point, we've moved our current pointer over until we found the node that we want to delete. So current is over the node we want to delete, previous is the node behind the node we want to delete, and next is the node after the node we want to delete. So now we need to move our pointers around. So essentially, the first thing we can do is we can move previous's next pointer to basically ignore current and point to the next node after current. So we can say previous.next equals next. So we are taking that previous's next pointer and ignoring the current node. Now we need to say next.previous equals previous. So basically taking the next node's previous and pointing it to previous. That's pretty straightforward. We're removing all references to the current node, to and from it, essentially. So one thing we need to be careful for here is next.previous equals previous. Next could be null. For example, if we're trying to delete the node at the very end of the list, current would have a value, but next would be null. So next.previous would throw a null reference exception. It wouldn't know what to do with that. So we need to make sure next actually has a value. So let's say if next not equals null, then we attempt to move the previous pointer to previous. Okay, I think that should cover delete. So let's test it out. So let's go down here. Let's say so we have 1, 5, 8, 10. So let's see how our list looks now. So 9,000, 1, 5, 8, 10. So let's say we wanted to delete 9,000. So let's say list.delete 9,000. Let's run this again. All right, we have 1, 5, 8, 10. We no longer have 9,000. So let's say we wanted to delete 10, the last element in the list. List.delete 10. We have 1, 5, 8. And let's try to delete 5, the element in the middle of the list now. List.delete 5, 1, and 8. Okay. Delete seems to be working. All right, so we have prepend, we have append, we have print and delete. Now let's go over search. Search is going to take in a value and it's going to search the linked list for that value. So let's go ahead and write our search method. So let's say search. We're going to pass in the value that we're looking for, and we're going to want to iterate over this list. So we're going to need some kind of a current pointer to point to the current node. So let's say let current equals this dot head. So we're going to start at the head, and let's start iterating over the list. So let's say while current not equals null. Now inside the body of this loop, we're going to check to see if the current value is the value we're looking for. So let's say if current.value equals the value that we passed in, the value that we're looking for, then we found the node. So we can just return current. Else, if current's value isn't the node that we're looking for, isn't the value that we're looking for, we're going to want to just move on to the next node. So let's say current equals current.next. Okay, and that'll keep iterating over and over until it finds until it finds a node with the value that we're looking for. If it gets to the point where it's outside of this while loop, then we didn't find the node that we were looking for. It doesn't exist in this list. So let's just return null in that case. Okay, cool. So that is search. So let's test it out. So let's get rid of these delete calls, and let's print out our current list here. So 9,15810. All right, so let's search for, let's say 5. So let's console log list.search 5. It should return us the node with the value of 5. And as you can see, it did that. It returned us the actual node object with the value, the next node, and the previous node reference. Okay, cool. So let's see what happens if we search for a value that doesn't exist in the list. So let's say 25. Let's run this again. And we have null here. It tried to go through the list. It didn't find 25. So it just returned null. And that's pretty much it for search. And that's pretty much it for linked lists. I hope you liked this video. If you did, leave a like. Be sure to subscribe if you want to stay updated with my content, my future videos in this series. Merch link is in the description. But other than that, peace.